All right, good morning, team. So we have one day to prepare for our science exam tomorrow. So we're going to start out with a little bit of review. Go ahead and put your name and date at the top. Again, we only know that there's one best house in all of America and Africa, and that's Bridges, but you can put your house here too. So follow the directions on the screen. It says write the letter from the cell analogy. Remember, we learned that word last week that best represents the organelle under the cell parts list. So we have all of our cell parts here. We have our analogies that represent the cell organelles here. You're going to take the next 2 minutes to match the correct letter with the correct cell part. Go ahead and put your thumb up right now so I know that you are trying this on your own first, and hit the pause button. If I do not see thumbs up, I'm coming around, Mr. White is coming around, and it will be a demerit if you're just copying me, because that's not learning, it's just cheating. Okay, good. All right, ladies and gentlemen, we're going to go over our answers very quickly. So for the first one, it was cell membrane. I will accept A or J. A is the city limits or border. J is the toll road. The big thing for cell membrane is that we want to remember that it is semi-permeable. And make sure your paper looks like mine, which means that some things come in, but others are left out. All right, let's go to number two. Number two says cell wall. We said K, which is the wall around the city. Number three is cytoplasm, which is L, the atmosphere or air that we live in. Nucleus is going to be B, which is the city hall or mayor's office. Mitochondria is H, which is the power plant. Lysosome is I, which is the waste management or recycling plant, and the vacuole is D, which is the storage center. If we take a look at the bottom, we have the experiment that was on our assignment from last week. What I noticed is that we had some difficulty identifying the independent and dependent variables, so we're going to do this together. So it says write the independent variable, dependent variable, and two controlled variables of this experiment below. You'll notice this looks a lot like ST Math, no words. Okay, well, there's words right here, but you get what I'm saying. What we need to do first, we have our circle and square. We know that the circle is always our independent variable. This is what we changed on purpose. Go ahead and fill that in. And the square, or the effect of the experiment, is the dependent variable. And this is what we measure. So the independent variable is what we change on purpose. What you need to do is actually look over this experiment right now and take a look. What is the thing that the scientists changed? Excellent. If you identify that they changed the amount of fertilizer, you are correct. We see here there's 0 drops of fertilizer. Here there's 2, 4, and 6. So each plant has a different amount of fertilizer. Now, if we go to the dependent variable, this is what we're measuring. So you now have to make an inference based on these different amounts of fertilizer. What do you think the scientist is trying to measure? Take the next 10 seconds, write it down here. I'm going to write mine down as well. Make sure you're writing in a complete sentence. Five seconds left. All right, on. Oh, why y'all ain't tell me I was showing my answer? Bombs? Okay, here we go. So you already saw it, so I'm just going to show it to you. Boom. The scientist is trying to measure the growth or height. I'll accept either one of the plant. Okay, now this is the tricky part. Now we need to move to the controlled variables. I want you to circle controlled variable and write stays the same. In order for this experiment to be fair, in order for it to be valid, in order for it to just actually make sense, we can only change one thing. And we've already identified that the thing that we're changing in this experiment is the amount of fertilizer. So what are some of the things that the scientist actually needs to keep the same so that his results are valid? If you look in this image, there are 3 things that jump out at me that have been kept the same. I want you to circle those 3 things on your paper right now. I'm going to do the same. All right, we're going to show our answer. Ooh, don't look at my nails. I'm sorry. Oh, I already know Ranjay running her mouth like, oh, look at this. Okay, whatever. I'm going to go get them done tomorrow. Here we go. 1, 2, 3, boom. 3 things that jump out at me immediately. Plants have to receive and make your paper look like mine the same amount of sunlight. Plants need to receive the same amount of water, and they're going to be in the same pot, or we can say that they're going to receive the same amount of soil. Now, there's a few others that you may also include. So the same type of water, the same brand of soil, all of those are also acceptable. We're going to rewrite our controlled variables down here at the bottom. So the first is the same amount of sunlight. The second is going to be the same amount of water. These nails are really embarrassing. Oh my goodness. And the last piece is going to be the same, we'll say same amount of soil. Excellent job. Now, it is super important for your paper to look just like mine. On tomorrow's exam, there's only 2 questions about variables, but I want to make sure that we get those 2 questions right. If you need to pause the video right here to get these answers down, go ahead and do it. If not, we're going to turn the page. All right, so this is one more piece of review from last week. Let's read this experiment together. When I pause, you fill in the blank. Nope, you actually need to fill in the blank, which means it's like Dora the Explorer. You're going to whisper into the computer. Now she's like, swipe or no swiping? Say it with me. This is just like that. Don't worry, I still know that you watch Dora. It's cool. Little Michael performed an experiment where he wanted to measure how the, no, seriously, say it, temperature, very good, of the water changed based on how much water there was in a beaker. He took 2 different sized beakers full of water and left them out in the sun. What was his independent variable and dependent variable? Right now, I want you to circle the independent variable in the text, and I want you to put a square around the dependent variable in the text. Go ahead and take 10 seconds to do that right now. Awesome. So if I'm looking here, what we changed on purpose, it says, and our keyword is different. So different size beakers full of water, which means that we're going to have different amounts of water. And he's measuring, and it even gives us the hint because it says measure the temperature of the water change. So we're measuring the temperature. So the independent variable, we're going to keep rewriting it. This is what we, change on purpose. And what did we say we changed on purpose? Excellent, the amount of water. Now, if we take a look at our dependent variable, we're going to rewrite again what that means, and this is what we measure. Very good. I only heard like 2 people say it. It was like Demyron and what's his name? Kesley. Remember, this is the effect. We're measuring the temperature of the water. Awesome. Now we go down below at the controlled variables, and this stays the same. What are our controlled variables here? Now, in order for you to get this, you're going to actually have to picture this experiment. So let's actually say I gave little Michael these 2 different beakers. They have 2 different amounts of water, and he sets them outside. What is something that has to stay the same? Let me pose a question to you. Would little Michael be able to put 1 beaker right outside the door in the shade and 1 in the neutral ground in the middle of St. Claude where there's always direct sunlight? Absolutely not, because of course the temperatures would be the same. So one of our controlled variables is that these beakers have to be in the exact same location. In the same location. Awesome. And then when we think about the substances that are actually in these beakers, what's something else that has to be the same? Could I put salt water in one, Kool-Aid in another? Oh, okay. Could I put sugar water in one and lemon water in another? Oh, okay. So the second control variable is that we have to have the same substance in the beaker. Remember, in order for an experiment to be valid, in order for it to make sense, we can only change one thing. The one thing that we have changed is the amount of water. So all other factors have to be controlled, have to remain the same. So I gave you a little bit of information. You're going to answer questions 1 and 2 on your own. Take 3 minutes to do that right now. Make sure you are writing in a complete sentence. Go ahead and put your thumbs up. So Mr. White and myself know that you are working independently. I'm going to pause the video here. Go ahead and get started. All right, we've answered both of these questions. Why do we need to control the two variables above? We need to control these variables because if Lil Michael puts the beakers in different locations, this will affect the water temperature and make the results invalid. What might happen if Lil Michael adds salt to one of the beakers? If Lil Michael adds salt to one of the beakers, we won't know if the salt also has an effect on the temperature, so his results will be invalid. Remember, experiments are only valid if we have one independent variable. That's one independent variable. I'm going to say it again, one independent variable. All right, excellent job. If you need to pause to get these answers down, go ahead and do that. If not, you can turn the page with me. Let's take a look at our focus today. In your reading intervention class, you should have watched a video about diffusion. We're going to go over diffusion and osmosis right now. So diffusion, this is the spontaneous. When we say spontaneous, it means that there's no pattern. It's random. Things are moving all over the place. So no pattern, it's random. So the spontaneous movement of a substance from a region of higher concentration to a region of low concentration. So what does that mean? If we are at a party and this is the food table and all of these dots represent all of the people at the party. Eventually, all of these people are going to start to get kind of hot. So what's going to happen? They're going to move from an area of high concentration, HC, to an area of low concentration. So there's more room where they can move more freely. That's all diffusion is. Atoms, molecules are moving from an area where they're grouped together, where there's more space for them to spread out. Let's take a look at osmosis. Osmosis is the passage of water from a region of higher concentration, so we see that same phrase, through a semi-permeable membrane, a region of low water concentration. So now we have some things that we need to focus on. Diffusion is just the movement of molecules or atoms out in the open. They don't have to cross over anything. So let me give you an example. I'm at Miss Martinez's house right now. Literally, this is her table. You want to see it? It's beautiful, wood grain. Now, see, I told you she was here. Now, if I pass gas right now, okay, hold on. Wait for it. Wait for it. Oh my God, that's so nasty. That's diffusion, guys. You can smell it. Okay. So what happened is that my gas molecules, those nasty gas bubbles, actually diffused across the room in spontaneous movement all the way over to her nose. But osmosis is slightly different. Osmosis would be if I have a container of salt water and I drop a cell into this salt water. Water is going to move from an area where there is a high concentration of salt to a low concentration of salt. We're going to see how this works in just a minute. Okay, let's take a look at these questions. So it says, look at the notes above. What does the term diffusion mean? I want you to rewrite this definition in your own words. Look at the notes above. What does the term osmosis mean? Again, look at the notes. Write your definition here. What is the difference between diffusion and osmosis? Based on your observations, I want you to focus on this little guy right here, okay? So I'm going to give you 5 minutes. Go ahead and answer questions 1 through 3 right now. Go. All right, guys, 1 and 2 are very simple. So diffusion, the movement of molecules or gas from an area of high concentration to a low concentration. Osmosis is the movement of high water concentration across a semi-permeable membrane, low water concentration. So when I think about osmosis, I think about having a cup of Kool-Aid, and the Kool-Aid is just way too sugary and too strong. So oftentimes, what do we do to Kool-Aid that's too strong? We're going to add in some water. And so as we go through this lesson today and you're thinking about osmosis, you're going to think about water moving to an area where there's less water. We want to dilute the substance, or we want to add more water where there's more salt, or we want to add more water where there's more sugar. We're going to see that in just a second. So what is the difference between diffusion and osmosis? The big difference is that one allows molecules and gas to move freely, and the other requires movement across a membrane, specifically a semi-permeable membrane. And that just means that semi-permeable means that some things can come in, but other things are going to be kept out. But if you need to pause to fill in the blanks here, go ahead and do that. If not, turn the page with me. So evidence dive 1, we see that this is clearly osmosis. We know it's osmosis because we have the presence of a semi-permeable membrane here. So what we are going to do is answer all the questions on this page. You're going to try it on your own first, and then I'm going to help you out. So it says, write one statement comparing the two images above. Write one statement contrasting the images above. Describe the movement of the solution in the image to the left, which is going to be over here. What does the dashed line in the middle of the solution represent? So what is this middle piece called? And why does the movement in the solution stop? Why don't we see arrows on this right side? Okay. Take 2 minutes, answer these questions on your own. Go ahead and put thumbs up. Ready, set, go. You're going to see that I added some notes to the top of the image, and I want to point those out to you at this time. So if you notice, these dots inside of the solution are solute or salt. The salt is being put into the water so that it hopefully dissolves or is dissolved by the water. If you look at both sides of image 1, which side has a greater amount of salt? Good job, the right side here. So because of that, there's actually a higher concentration of water on the left side than there is on the right side, because the right side actually contains more salt than it does water. So we know that in osmosis, water moves from an area of high water concentration to an area of low water concentration. We don't want this side to taste as salty as it looks, so the water is going to come over here to dilute this solution. So if we look over on the right side, even though the water level went down here, the solution has been equalized. And it's been equalized because for the amount of salt that was on this side, now there's a higher water concentration making this balanced. And this side is also now in balance, which is why the movement has stopped. So let's take a look at our questions. It says, write one statement comparing the two images. Both substances contain water and salt. One statement contrasting the images is that in the image to the right, we see that the water level is lower on the left side of the image. Describe the movement of the solution. Well, the water is moving from an area of high water concentration to an area of low water concentration. Take a look. This side has 70% water. This side only has 40% water. So we want to balance these out. What does the dashed line in the middle of the solution represent? This is our semi-permeable membrane, and that's how that water is able to flow across. Number 4, why does the movement in the solution stop? Well, it stops because we reach equilibrium or we reach a balance. Now, what did we learn from the image above? Write down 3 key points below. Let's do this together. The first thing we learned is what we learned from the previous page is that water moves from an area of high water concentration to low water concentration. Once the water reaches equilibrium, osmosis stops. And what I want to point out is that the movement of the molecules doesn't stop. These molecules are going to keep moving on this side. These are going to keep moving around on this side, but they're no longer going to pass back and forth across the semi-permeable membrane, which leads us to point number 3. Osmosis is made possible by a semi-permeable membrane. I know that's a lot of information. You guys did a great job. If you need to pause the video here to get these responses down, go ahead and do that right now. Excellent, excellent job. We're going to turn the page. Again, if you need to get these down, pause the video here. All right, let's take a look at the image here. So we see that this is very similar to the image on the previous page. Stop focusing on my nail. Like I said, I'm going to get them done. So in the middle, we have a semi-permeable membrane that's dividing this beaker. And remember, all of this is a model of what happens with the cells in our body and the concentrations of water and salt outside of our cells and inside of our cells. But we'll get to that in a second. So on this diagram, you see I've labeled a few things. I want you to label those on your paper as well. These tiny spheres are salt, and then the solution that the salt is in is water. And so if you look on the left side and the right side, well, which side contains more salt? Excellent. We can see that there's more spheres over here. So this side is super salty. And on this side, it is super watery. So we've labeled that this right side has about 80% of water for the solution, and this side is 20% water. Now, sometimes it's easier to think of these as two separate cups. So for this cup, based on how much salt is in this solution, it's only made of 20% water. And if we do the other side, based on the amount of salt that's in this solution, this is about 80% water. So if this were a glass of Kool-Aid, we'd be like, ooh, let me get some more sugar. And if this were a glass of Kool-Aid, we'd be like, ooh, let me get some more water, because it's like, oh, sugar. Now, let's see how osmosis works. It says water moves towards the high solute concentration. Remember, we talked about this. Water likes to move in osmosis in the same way of if we were watering down Kool-Aid. Wherever there's more salt or more sugar than water, water wants to move to dilute it. So if we look over here, we see that the water level actually went down on the right side and moved across the membrane to this side. For the amount of salt that's in the solution, now there's just as much salt as there is water, so it's 50-50. And if we look on this side, for the 1, 2, 3 spheres or molecules of salt, now the amount of salt and water is balanced, and this is also at 50-50 or equilibrium. So let's take a look at our notes up here. A solute is a solid that has been dissolved in a liquid solution. So again, our solute in this example is the salt. If we mix salt and water or sugar and water, the salt and sugar would be the solute and water would be the solvent, the thing that's doing the dissolving. In the image to the left, the circles are the solute. In osmosis, water rushes to the higher concentration of solute. Remember, we want to water it down. So now I'm just asking you some review questions. Is there a higher concentration of solute on the left or right side of the solution? As a result, where will the water move? You're explaining these two in your own words. Then go to number 1. In a cell, the semi-permeable membrane is the, pick the correct answer here. You have 2 minutes. Give me a thumbs up so I know you're answering these questions on your own. Go. All right, let's take a look at our answers here. So is there a higher concentration of solute on the left side or right side of the solution? We have already named that there's a higher concentration of the solute or the salt on the left side, which is here. As a result, where will the water move? We know that because there's a higher concentration of salt or solute on the left side, it means that there's a higher concentration of water on the right side. The water is going to move from an area of high water concentration to low water concentration, which means it's going to move from left. Yep, Mr. does not her left from right to left. So make sure you have that correct, because I think I wrote it wrong over here. From right to left. Alrighty. So in a cell, the semi-permeable membrane is your options were vacuole, mitochondria, cell membrane, cell wall, and chloroplast. If you haven't, make your paper look like mine, so we begin to associate sticky definitions with these words. It's not the vacuole because we know that's used for storage. It's not the mitochondria. We know that that's used to make energy. We know it's not the cell wall because the cell wall lets nothing in and out. And we know it's not the chloroplast because the chloroplast absorbs sunlight. So even if we use process of elimination, we know that it's cell membrane because cell membrane lets molecules and gas in and out of the cell. If you need to pause the video to get these answers down, go ahead and do that at this time. If not, you can turn the page with me. So now you are officially on your own. We like to call this as teachers independent practice. So you're going to take a look at the image here. It's just like the one that we did on the previous page. And I want you to explain to me, why is the water moving to the left side of the solution? So why do we see these arrows going from the right side to the left? Then you're going to look down at the bottom, and now it's time for the real world scenarios. If we drop a cell, or if there's a cell in our bloodstream right now, like there really are, and our cell contains 10% salt, but the water outside of our cells contain 20% salt, where will the water move and why? So this is an image of that 10% salt inside our cell, 20% salt outside. And this is what the cell looks like once this movement happens. So all you're doing is explaining in words what you see here. Go ahead and take 3 minutes to get that down. Go. All right, team, let's take a look at the answer. So it says, why is the water moving to the left side of the solution? What Ms. Tucker wrote is that the water is moving to the left side of the solution because there is a higher concentration of solute on the left side, which means there is a higher water concentration on the right side. We know in osmosis, water moves from high water concentration to low water concentration, causing the water to move from right to left. If you have something that sounds like that, you can leave it. If you need to adjust your answer, go ahead and do that at this time. So again, what we're answering here is, where will the water move in this picture and why? We know that the water will leave the cell because there is a higher water concentration inside the cell versus outside the cell. Due to the water leaving the cell is actually going to shrink or shrivel up like a raisin, because that water that's plumping the cell up is now being released across that semi-permeable membrane, and that cell membrane is the outline of the cell. All right, if you need to pause the video here to get these answers down, go ahead and do that. If not, you're going to turn the page with me. I love you guys, but I am leaving you all alone for evidence dive 4. So what you need to do is take a look at the image, read the questions, and answer them in a complete sentence. Good luck. Go. All right, guys, let's go over our final evidence dive before we take our exit ticket. So it says, where is the highest concentration of solute found in image 1? The highest concentration of solute is found inside of the cell. We see that there's 20% salt inside the cell, but only 10% salt outside. There's 10% salt outside. Know that there's a higher concentration of water outside of the cell than inside of the cell. So what happens to the cell when the concentration of solute, remember that's just the salt, is higher inside of the cell than outside of the cell? It means that the water that's outside in a high concentration is going to flood across the membrane into the cell where there's a lower concentration. So the big thing is that this is what we call a hypotonic solution. If too much water enters the cell, that cell is going to plump up, and eventually that membrane could break, which we call the cell being lysed, or the cell bursts like a balloon. We don't want that to happen. When that happens in our bodies, it could lead to huge problems for us, our organs, and our tissues. Let's take a look at the bottom. It says, go back and review evidence dive 3. What is the difference between a hypertonic solution and a hypotonic solution? So let's go over this. A hypertonic solution occurs when water leaves the cell, a high concentration of solute outside of the cell, causes the cell to shrink. So again, I have a cell, concentration of solute is higher outside, so the water inside of the cell leaves, and then that cell shrinks. In a hypotonic solution, there's a higher concentration of solute inside of the cell. This causes the water outside of the cell to move into the cell. I know I'm saying cell a lot, I just want to be thorough. If too much water enters the cell, it could lyse, and this means burst. So in hypotonic, there's all this solute inside, so water begins to enter the cell. It gets bigger and bigger. Eventually, that membrane could burst or lyse. Excellent job, guys. You will go to Illuminate right now. You are looking for your diffusion quiz on Illuminate. It should take you about 10 minutes to finish it. You'll know that you are taking the right quiz because number 1 will look like this. All right, great job today. Make sure that you are respectful, responsible, and resilient, and you are doing everything you can to earn your respect letters. Friday's party for our winning house is going to be incredible, so don't miss out on that opportunity. Have a great day, guys.